Okay, so good evening, everyone. Someone sent me a good evening by private chat, so good evening to that person also. Yeah, I'd like to encourage people to whatever they want to write or whatever they want to ask. There's nothing bad if you mention those things in public. I mean, in public, in chat publicly. Okay, so let us begin. Welcome everyone to the sixth lecture of this course. So I just want to quickly recall what we did last time, or one of the things that we did last time. So I hope everyone is able to hear me and see my slides. So, okay. So one of the things we did last time was to discuss the gamma function. And I had said quite a few things about the gamma function, but let's just ignore all that for today's lecture. And let me just extract the main property that we needed. So we defined a function gamma. So actually we defined it on the complex plane, and it is a complex valued function. But for now, so we define gamma, let's restrict our attention to real numbers, where it is a real valued function. So gamma is, we defined a map from the real numbers minus the set of the following integers, 0, -1, -2, and so on, to real numbers, such that, so if p is strictly greater than 1, then the value of gamma p is given by this integral 0 to infinity, t to the power p minus 1, e to the power minus t dt. And for other values of p, uh, the value of gamma is given by this formula. We can apply this formula repeatedly. Apply repeatedly if p is less than or equal to 1, let's say. Okay. And one of the properties of the gamma function that we will need is that gamma of p is never 0 for any p in the real numbers -0, -1, -2, and so on. Okay, so with these, once we have a function which satisfies these properties, we consider the inverse of that function. So that function is not defined at 0, -1, -2, and so on. So we define a map psi from R to R given by psi of p is 1 upon gamma of p if p belongs to the real numbers -0, -1, -2, and so on. And at these non-positive integers or negative integers union 0, so p belongs to z less than or equal to 0. So integers which are less than or equal to 0, we define psi of p to be 0. And the main point is that this function psi is a very nice function, and psi vanishes only at the set z less than or equal to 0. So it vanishes at the set z less than or equal to 0, and it never, so it does not vanish at any other points. Okay, so this is something from the previous class which I wanted to recall. Okay, so let's go ahead. And this is the summary of what we did in the previous class. For any real number p, we define j of px to be summation n going from 0 to infinity, 1 upon n factorial minus 1 to the n, and this factor. Okay. So times x by 2 to the power 2n plus p. So the above is a well-defined power series once we know that the gamma function never vanishes. So yeah, so since the gamma function, so this is, I can rewrite this as in the notation that I used in the previous, on the previous page. This is minus 1 to the n factorial into psi of p plus n plus 1, right? To the power 2n plus p. So since this psi is, I mean, I'm just, in this point, I'm just trying to say that this psi, this is actually a real number. It's not infinity or anything. And if p does not belong to this set 0, 1, 2, and so on, then j of p and j of minus p are the two independent solutions of the Bessel equation. And if p belongs to 0, 1, 2, and so on, then j minus p is equal to minus 1 to the power p jpx. So I had left this as an exercise. And this uses that if p belongs to 0, minus 1, minus 2, and so on, then psi of p is equal to 0. So this was the main point behind this exercise. Okay. So anyway, so this was, we saw this last time, and we did not, we did not, in this, we did not look at how to get the second solution. Uh, it's a horrible calculation. Well, if not horrible, it's definitely not very pleasing. And we skip that, but it's written, but it's given in the notes in great detail. So those who are interested can look at it. Okay. And then we saw what the Bessel identities are. So let's just pause at this slide for a few seconds. Okay. So let me go ahead. So let's see some interesting consequences of the Bessel identities. So let's look at this problem. So I don't think this assumption is needed. Let p greater than 0, this is not needed. So we have to show that between any two consecutive positive zeros of jpx, there exists precisely one zero of jp minus 1x and precisely one zero of jp plus 1x. Okay. So we are taking jpx. So this is, if we make the graph of jpx, the graph will be something. And if we take any two consecutive positive zeros of jpx, sorry, right? So if my jpx vanishes at, okay, so I have to use the notation c and d. If these are two consecutive zeros of jpx, then there is a zero of jp plus 1 between c and d. So that's the statement of the, and there's exactly one. Okay, so how do we do this problem? So let c and d be two consecutive zeros of jpx, and let's assume both of them are positive. So we look at this function x to the power p jpx. This vanishes at c and d because jpx vanishes at c and d. And therefore, by Rolle's theorem, so if I have a function which vanishes at 2 points, then by Rolle's theorem, its derivative vanishes at least for 1 point. So that's like intuitively, the idea is very simple. So the graph of the function will look like this, or it'll look like this. But anyway, the point is that at some point, it'll vanish, the interval, the derivative. So this function x to the power p jpx vanishes, and so its derivative is going to vanish at some p in c and d. And this follows from the best. This is one of the Bessel identities. Bessel identity, right? So, and this vanishes at b. That's what we just saw here, and therefore this thing vanishes. Since b is positive, it means that b to the power p cannot vanish. Therefore, we get that jp minus 1p, jp minus 1 of b is 0. And we can repeat the same argument as above with p plus 1, and instead of this identity, we have to use this one, right? Sorry, we just use this identity, and we will get that jp plus 1 has a root in c and d, c comma d, in that interval. Okay. uh, Thus we have proved that both uh, okay, I'm sorry, I think I have gotten the handout file, so that's not correct. So let me just close this file. Sorry. Okay, I'm sorry about that. So let's go ahead. I hope everyone can see my presentation. So thus we have proved that both jp minus 1x and jp plus 1x has at least one root in the interval c comma d. And now let's prove that it has exactly one root in the interval c comma d. So if jp minus 1, if jp minus 1 has two roots in the interval c comma d, so what do we have? So we have jp, sorry, right? So we have this function jp minus 1, and let's say it has two roots, c and d. So this is c and d, and let's say it has two roots here and here, right? Then by applying the previous what we just saw to jp minus 1, then that it'll mean that jp equal to jp minus 1 plus 1 has one root over here between these two roots. Let's say alpha and beta are the roots of jp minus 1, right? But that's a contradiction because we had assumed that c and d are successive roots of jp minus 1. Jp, sorry. Right. So let me just repeat this argument. I think I did not say this correctly. So we are taking two successive roots of jp, this c and d. These are roots of jpx, right? And we saw that jp minus 1 has at least one root. So let's say this root is alpha over here between c and d. And let's say now it has two roots, alpha and beta. So I'm saying that applying the same reasoning that we applied to jp, we get that jp now will have a root since these are roots of jp minus 1. We will get that jp has a root over here, but that's a contradiction because c and d were taken to be successive roots of jpx. There's no roots. By assumption, there were no roots of jpx between c and d. Okay, so I hope this is clear. It's a fairly simple argument. So therefore, jp minus 1 has exactly one root in the interval c comma d. Okay, so let's go ahead. Similarly, jp plus 1 has exactly one root in c comma d. All right. So that completes the proof of this result. So that's exactly what we wanted to prove. So we had to show that between any two consecutive positive roots of jpx, there exists precisely one root of jp minus 1 x and precisely one zero of jp minus 1 x and precisely one zero of jp plus 1 x. Okay. So let's go ahead. So here's another example of a question. So we have to find a and c so that j2x minus j0x is a times j double prime cx. Yeah, so c is coming over here. Yeah, c is coming here. Okay, so once again, we have to use the Bessel identities. So a and c both are scalars, so a and c are in real numbers. Okay, so we first use jp minus 1 x minus jp plus 1 x is equal to 2 j prime p x, and we take p equal to 1 in this. So this is, I suppose, this is one of the last ones. So yeah, so here we are using this identity. So jp minus 1 x minus jp plus 1 x is equal to 2 times j prime px. So we put p equal to 1 in that. So we get j0 minus j2 is equal to 2 times j1 prime x. And now we use, this is one of the first two identities, x to the power minus p, jpx derivative is equal to this thing. And we put in p equal to 0. So then when we do this, we get j0 prime is equal to minus j1 x. So when we differentiate both sides, so remember we have j1 here, and we want to make this into a second derivative because we want a second derivative here. So we differentiate both sides. So we get j2x minus j0x is equal to minus 2 j1 prime x, which is equal to 2 j0 prime prime x. Okay. So this is also fairly easy. It's just a consequence of the Bessel identities. Hence A is equal to 2 and C is equal to 0. Okay. And we can use these. So we have these three relations. And to see that JPX are elementary functions. So I haven't defined what elementary functions are. So I will define them in a future slide. I mean, I will define them one slide later. So I'm sorry about this. So uh, let me just go ahead and define elementary functions first. So, okay. So an algebraic function is any function y of x, y is equal to f of x, which satisfies an equation of the form Pnx y to the n plus Pn minus 1x y to the n minus 1 dot 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 plus P1x y of x plus P0x is equal to 0 for some n where each Pix is a polynomial. Okay, so for instance, I could take any polynomial x square plus 5 y cube plus x cube plus 3x plus 17 y square plus x to the power 100 plus 2 plus 2 pi x to the power 17 plus pi square is equal to 0. Yeah. Suppose I take a function y which satisfies this equation, then I will call such a function an algebraic function. Okay. And this can be any end. It does not have to be 3. I mean, I can cook up as many horrible examples as I want. Yeah, whatever. Okay. So I hope the point is clear. So such functions are called algebraic functions. So, uh, yeah, the space of all real valued functions, or let's say if I take any interval, let's say I take any open interval, then the space of all functions from I to R is a huge set. So inside that set, from that set, we form, this is the subset of algebraic functions. So this is a very small set in comparison to that set. So for instance, we could take a simpler example instead of this complicated example. We could take a function which satisfies this equation, x cube. Okay, so instead of this, let me write, we could take a function which satisfies this equation, right? Y square is equal to x cube, right? So basically this function is y of x is equal to x to the power 3 by 2, right? So let's say we can define this function on R positive, right? So here my Pnx, so I can rewrite this as y square minus x cube is equal to 0. So here my P2x is 1, is the constant function 1. P1x is 0 and P0x is minus x cube. Okay. So yeah, so I mean, we can get many nice simple functions as algebraic functions. So, okay. So take algebraic functions, trigonometric functions, so sine, cos, tan, inverse trigonometric functions, sine inverse, cos inverse, tan inverse, exponential and logarithmic functions. Okay, so yeah, so I've made some corrections. So I'm sorry, I had made some corrections, but I think yeah. So this is, I mean, I'm just taking the functions e to the x and log x. Okay. And all other functions that can be constructed from these functions by adding, subtracting, multiplying, dividing, and composition of functions. All right. So I'm taking all algebraic functions. So these, as you saw, are functions of the type x to the power 3 by 2 or x to the power 5 by 2 plus, I don't know, x to the power 17 by 2 plus 17. Whatever. You can cook up any algebraic functions. And you take algebraic functions, trigonometric functions, exponential functions, the exponential function, the logarithm function, and we construct the set of all functions which can be cooked up out of these. So any function which can be that set will be called the set of elementary functions. Okay. So in other words, we have all these nice simple functions which we are very familiar with, and we tell ourselves that, okay, let's look at the set of functions which can be constructed from these functions. There are many more functions, but this is a particularly simple set. So there's an element, this set of functions is called the set of elementary functions. So for instance, this function is fairly complicated. There's a fairly complicated function, and we don't know where it will be defined, but okay, it will be defined, hopefully it will be defined from some non-empty interval to the real numbers. But anyway, we can, yeah. So I hope it's clear what elementary functions are. Yeah, basically they are functions which are cooked up from functions which we are familiar with. And the point I'm making in this slide is that we can use these identities uh, repeatedly, these three identities. So we have to check j half is this thing. We have to check j minus half is this thing. And we can use this identity repeatedly. And we can check that for every p in of this form, z plus half. So we can take any integer n plus half. If p is equal to, if p is of this form, then jpx is an elementary function. Okay, so here are a few examples. So j3 by 2 is this thing over here, right? So this is an elementary function. And similarly, j minus 3 by 2 is this thing over here. So this is also an elementary function, because we can cook up this function from trigonometric functions and from polynomials and powers of polynomials and things like that. And I'm sure that by an easy induction argument, you can convince yourself that if p belongs to z plus half, I will leave this as an exercise, then jpx is an elementary function. Yeah, this will be an easy exercise which will follow by a simple induction argument. So these functions are called spherical Bessel functions, as they arise when solving wave equations in spherical coordinates. Okay, there's some stuff which is not so important. And these are slides which I've already done. So let me go. So this is the interesting theorem of Liouville. So he says that Jm plus half, these functions that we saw, are the only Bessel functions which are elementary functions. So let's just pause over here for a few seconds and try to appreciate this theorem. We defined these functions jpx as some horrible series, right? I mean, they were not very pleasing looking coefficients. Times 1 upon, I think it was gamma p plus n plus. So you should, I mean, this is like a really nice theorem. I mean, how would you prove that if p is of the form m plus half? Okay, how would you prove if p is of the form m plus half? Then jpx is a elementary function. That will follow easily from an induction argument using the Bessel identities. But the converse, if p is an elementary function, then p has to be of the type m plus half. I mean, if you pause and think about it for a moment, it looks like a very hard problem. So I don't know how this was proved, but I guess this result is very interesting. Okay, so let's go ahead. So that sort of finishes one part of our discussion for today. So it is rarely possible to solve second order linear ODEs in terms of familiar elementary functions. So you see, when we have a series, it's not really easy to say anything about the properties of the function. What can we say about the zeros, etc., etc. So if we can write something in terms of functions which are familiar to us, then it may be a little bit more easier to analyze them and their properties, etc. So how do we understand the nature and properties of these solutions? So it is surprising that we can obtain quite a bit of information about the solution from the ODE itself. And it is indeed very nice and interesting. And that's what we are going to see now in the rest of the lecture. So let's look at this. The first theorem we are going to prove today is the Sturm separation theorem. So it says that if y1x and y2x are linearly independent solutions of y double prime plus p of x, y prime plus q of x, y is equal to 0. So this is an ODE. And p of x and q of x are given to be continuous functions on this open interval a comma b. Then y1x and y2x have no common 0 in the open interval ab. I mean, that's already quite surprising, right? Because given this differential equation, it'll have some solutions. And I mean, we can pick up any yeah, it'll have a two-dimensional space of solutions. So we can pick up any two solutions, and this first part is saying that they don't have any common zero in a comma b. And the second part is saying that between any two successive zeros of y1x, there is exactly one zero of y2x and vice versa. Okay, between any two successive zeros of y2 of x, there is exactly one zero of y1 of x. So if you stare at this statement for a few seconds, I mean, yeah, at least I would be quite surprised. I mean, how can you say such a strong statement? But you will see that the proof is remarkably easy. So let's first prove the first uh, statement. Let us consider the Wronskian. So this is something which you should have learned in your MA 108 course. So is this is the function which is defined to be the determinant of y1x, this matrix. Okay. So it satisfies the differential equation. So when we differentiate w, we get minus p of x w of x. So this is an easy check. So you have to use the fact that your y, it satisfies this differential equation. When you use this, then you can check this easily. And we know what the solutions of this differential equation are. So it's given explicitly by this. So w of x is this function. So we can choose any. So p and q are defined on the open interval a and b, and they are continuous there. So we can choose any a naught in this a comma b, and we can write w of x is equal to this thing. And there is some constant c. For some constant c, I mean, c is in fact w of a naught, right? Okay. So in particular, since y1 and y2 are linearly independent, the Wronskian is non-zero, and so it never vanishes. So this proves one, right? So yeah. So the point, yeah. So since y1 and y2 are linearly independent solutions, this determinant is not identically zero as a function. Yeah, this Wronskian that we wrote. This is not identically zero. And from this, this is our w, and from here it's uh, so what I'm saying is w is zero at a point in a comma b if and only if it is identically zero. And since we are taking y1 and y2 to be linearly independent, it is not identically zero. That therefore it's never zero, right? So, but on the other hand, if y1x and y2x had a common zero in this interval a comma b, let's assume that this is not true. Y1x and y2x have a common zero. That would mean that y1x this term vanishes, and it would mean that y2x this term vanishes, right? That would mean that the Wronskian vanishes, but we know that's not true. So and we get a contradiction. So therefore, y1x and y2x, they have no common zeros in the interval a comma b. So that proves one. So I hope that is clear. Okay. Uh, let's go to the proof of two. So let's look at the statement once again. Between any two successive zeros of y1, there is exactly one zero of y2. And we can, of course, reverse y1 and y2 and do the same argument. So how do we prove that? So let's prove two. So let x1 and x2 be successive zeros of y1. First, let us show that y2 has at least one zero in the interval x1 and x2. So since this Wronskian, we just saw that it is non-zero. Therefore, it has the same sign in the interval ab as it never vanishes. So wx, so yeah. So thus wx1 and wx2 have the same sign. So we have, so our situation is a bit like this. So we have our interval a and b like this. Inside a and b, let's say this is x1 and let's say this is x2. Okay. So the Wronskian never vanishes. So w of x1 and w of x2 have the same sign. Uh, okay. So, we are assuming that, so remember w of x1 was y1 x y2 prime. Yeah, w of x1 is y1 x1 y2 prime x1 minus this thing, but we are assuming that x1 and x2 are roots of y1, so therefore this first term will vanish and only the second term will remain. This term is non-zero, so that would mean that y1, both these terms individually are non-zero, both these y1 prime x1 and y2 x1, because this Wronskian does not vanish. Okay, and the same argument holds here. Here w of x2, this is what I explained there, it's y1 of x2, y1 prime, I'm sorry, y2 prime of x2 minus y1 prime of x2, y2 of x2. But y1 of x2 is 0, so this term vanishes and only this guy remains. And this is non-zero, so this means y1 prime of x1 and y1 prime of x2 are non-zero. So let's go ahead. So it follows that y1 prime x1 and y1 prime x2 have opposite signs, since x1 and x2 are consecutive roots of y1. Okay, so what I'm saying is, so let's look at the graph of y1. So x1 is here and x2 is here, right? And y1 has no 0 in between. So its graph will, I mean, depending on whether it's positive or, yeah, its graph will either be this, like this, or it will be like this, right? So in any case, the slope, I mean, this slope, this direction of this slope and direction of this slope, they will have opposite signs. So that is this, what this statement is saying intuitively. Well, but I have written it follows. Okay, yeah, fine. Okay, and so since these two have opposite signs, so this and this have opposite signs, it will mean that y2x1 and y2x2 also have to have opposite signs, because if y2x1 and y2x2 had the same sign, then it will mean that wx2 and wx1 will have opposite signs. Okay, I hope that is clear. Thus y2x has a 0 in x1 x2. Yeah, so that proves it. So we have proved that this x1 and this x2, and y2x1 and y2x2 have opposite signs. So in particular, it'll have to cross this somewhere. So therefore y2x1. So therefore y2x has at least 1 0 in the interval x1 x2. So I hope this is clear. Let me just pause over here for a second, for a few seconds. If anyone has any questions, then they can ask me in chat. Okay, so there are no questions, so let's go ahead. So we have proved that between two successive zeros of y1x, there is at least 1 0 of y2x. So now we have to prove that it has exactly 1. So if y2x had two zeros in the interval between x1 and x2, let's say alpha and let's say x1 strictly less than alpha, strictly less than beta, strictly less than x2, then by the same, yeah, so what would we assume? We assume that x1 and x2 are successive roots of y1. So now let's say y2x has two roots, alpha and beta, right? Then we apply the same reasoning to y2 and we will get that there's some point over here at which y1 vanishes. Y1 is equal to 0 at this point, right? But that's a contradiction, because we took x1 and x2 to be x1 and x2, sorry, to be successive roots of this. So this completes the proof of the theorem. So let's just look at the theorem once again, this term separation theorem. So y1 and y2 are two linearly independent solutions of this equation. And first of all, they have no common zeros in the interval where this where P and Q are, where this equation is defined. And secondly, between any two successive zeros of y1, there is exactly one zero of y2 and vice versa. Okay, so this is a very interesting theorem. So let's go ahead. So as a consequence, if y1 and y2 are linearly independent solutions of y double prime p of x y prime plus q of x y is equal to 0, p comma q continuous on AB, then the number of zeros of y1 and y2 on AB differ by at most 1. Right. Okay, so this is like going to be a simple exercise in combinatorics, so you can just, yeah. So let's say this is our A and this is our B, and we are like, and let's say the graph of, this is the graph of y1x, right? So then, yeah, so y2x will have a 0 here, have a 0 here, have a 0 here, have a 0 here, have a 0 here. It, sorry. So can it, so maybe I'm wondering, can it have zeros here? So I'm wondering if this number should be made 2. Is this 1 or 2? So if it has a 0 here, okay. So I'm a little bit confused now. Should this be 1 or 2? At most 1 or at most 2, right? But surely we cannot have that y2x has a 0 here, because then our theorem will say that, oh, someone is telling me that 1 is correct. So, oh, okay. Oh, I'm sorry. Yeah. So, yeah. So, yeah, I'm sorry about that. Yeah. Thank you. Thank you for correcting me. Yeah. Right. So let's say how many zeros is it? Let's say we just have to count. This is 1, this 2, this 3, this 4, and this is 5, right? And this 6. So on the other hand, this will be 1, 2, 3, 4, 5, 6, and this will be 7. Okay, yeah, right. So, and yeah, if it was not 0 over here, then both of them have the same number of zeros. And if it was not 0 over here also, then one of them will have 6 zeros and the other one will have 5 zeros. Yeah. Thank you very much. Yeah. So I'm sorry. Yeah. So this is correct. So there's indeed a very nice theorem. Now let's just, so if you, let's try to see where we can apply this in amazing theorem, right? So we had looked at the Legendre equation, right? And the Legendre equation was defined on the interval -1 to 1. So we got a Legendre polynomial, which was like a really nice polynomial. But we know that the other series is going to be some horrible power series. So can we say anything about the zeros of the power series? A priori, when we saw the Legendre polynomial, there's no clue. We have no idea. But you must have seen in your exercise that the Legendre polynomial has n distinct roots, right? And then indeed that other horrible complicated series, we can say something about the roots of that series, right? So this simple theorem, which has, I mean, this very interesting theorem, which has such a simple proof, has a fantastic consequence. Okay, so let's go ahead. I hope the point I was making was clear. Okay, so in particular, either both have finite number of zeros or both have infinite number of zeros in the interval AB. Okay. Okay, great. So there's already a very nice theorem, but now we are going to see more interesting statements. So for further discussion, but now we need to modify our ODE a bit. For further discussion, we need that any ODE in the standard form, sorry. So this means why, yeah. So in this form, we can write it in the normal form. So we can convert it to an ODE of the type u double prime plus q of x u is equal to 0. So how do we do this? So we define v of x to be exponential integral a naught to x. So a naught is something inside a comma b, some point inside a comma b, right? So we define v of x to be exponential of this integral a0 to x minus half p of t dt. So this function, and we said u of x is equal to y of x by v of x. So y here is a solution of this equation. Y of x is a solution of this equation. Okay. Now notice that v of x never vanishes, right? So the zeros of u are in one-to-one correspondence with the zeros of v, with the zeros of y, right? And right now we are studying the zeros of y of x. So as far as the zeros are concerned, we can restrict our study to u of x. So that's a nice thing about this function, this trick. And one easily checks that u of x satisfies the following differential equation. So yeah, so here we set q of x is equal to this thing. So this q is this q over here, and this is a trivial check, so you can do it. And it is clear that the zeros of u are the same as those of y. That's something which I've already explained. And also note that, okay, yeah. So since we want this thing, right? We need this thing over here. So we need that p of x is once differentiable. So that, yeah. So let's just assume that p of x is twice differentiable. Okay. So that this q of x is a continuous function. Okay, but this is not so important. Yeah. I mean, most of the times we will be working with smooth functions. So yeah. So let's see this theorem. So let q of x be, okay, let me just pause at this previous slide for a few seconds. So all that we have done is we have made this substitution, and we observe that as far as studying the zeros of y of x is concerned, we are good. We just have to study the zeros of u of x. Yeah, because the function v of x, it never vanishes. Okay, so let's go ahead. So theorem, let q of x be continuous on the interval alpha comma beta. Let u of x be a non-trivial solution, means u of x is not 0. Non-trivial solution of u double prime plus q of x u is equal to 0 on a finite interval a comma b. So I just take any compact interval. So I take any closed interval a comma b, which is sitting inside alpha comma beta. So then this theorem says that u of x has at most a finite number of zeros in this interval. And hence the conclusion is that if u of x has infinitely many zeros on this interval 0 comma infinity, then the set of zeros of u of x is not bounded. So I have my u of x. So, and this is 0. So let's say my u, I know that the, okay, let's see the proof of the theorem first. It's easier to, yeah. So let's assume that u of x has infinitely many zeros in the interval a, b. So I have this compact interval, right? And here it has infinitely many zeros, right? And all this is defined in all this a, b, all this is happening in the domain where everything is defined, right? So out of this infinitely many zeros, I can find a sequence of zeros. I can find an x naught and a sequence of zeros xn, such that xn's converge to x naught as n tends to infinity. Okay. So first we want to show that u of x naught is 0, right? But u is a twice differentiable function, so therefore it is definitely continuous, and xn is converging to x naught. So uh, when we take limit xn tending to x naught, u of xn, and u of x naught is going to be equal to this by continuity of u, and each u of xn is 0, right? Therefore the limit is also 0, and we do the same thing for u prime, right? U prime at x naught is by definition this limit, and once again, yeah, all these are 0. Okay, so what does that mean? So since u of x naught and u prime x naught are both 0, it follows that the Wronskian at x naught is 0. Okay, but this is a contradiction, as the Wronskian at x naught is non-zero. So we can do it like this also. Uh, right, I think, but instead of saying it like this, I think a better way is to say that by the uniqueness of solution, we know that once we I mean, this is also correct, but I think this is a slightly better way to say it. By uniqueness, I know that once we specify these two values to be anything, there is a unique solution to this differential equation, right? So here we have found a solution such that u of x naught is 0 and u prime of x naught is 0. So this implies that u is forced to be 0, identically 0. But that is a contradiction because we started with a solution which is non-zero. Okay, so that is very nice. So it means that, yeah, on any bounded set, we cannot have infinitely many zeros. Okay, so I hope this is clear. So the next theorem is, let u of x be a non-trivial solution of u double prime plus q of x u is equal to 0. If q of x is strictly less than 0 in a comma b and continuous, well, we are always assuming continuous, then u of x has at most 1 0 in a comma b. Okay. So the previous theorem was saying that we have our alpha and beta, right? And we take, if we take any finite interval, then our u cannot like oscillate like this. Yeah, it has to be some, it can only have some finitely many zeros and then it'll go out. Yeah. So on the other hand, I can construct some horrible functions which oscillate like this, right? So I think, so if we look at this function, e to the power minus 1 by x square, I mean that bad function which we had constructed earlier, x not equal to 0 and 0 at x equal to 0. And if we look at f of x times sine 1 upon x. So my guess is that this will be a smooth function, but at 0, and it's going to oscillate like this, right? So yeah, so such a horrible, so this function in this compact interval, it will have infinitely many zeros, but such horrible things cannot happen with uh, with u if u is a solution of this differential equation. So that is what this theorem is saying. Okay, so let's go to the next theorem. So here, if we impose a certain condition on q of x, then we get that u of x has at most 1 0 in a comma b. So let's see how to prove this. I am running really slow. So let's assume that u of x naught is 0. Then u dash x naught is non-zero because of what we saw. If u dash x naught is also a 0, then u has to be identically 0. So let's assume that x1 is the next 0 of u after x naught. Okay. So, okay. If necessary, multiply by minus 1 and assume that u dash x naught is positive. All right. Uh, then u of x is strictly greater than 0 on x naught comma x1. Okay, yeah. So that's because, right. So this is our thing. Assume x1 is the next 0. So this is my x naught and this is my x1, right? And we are saying that u dash x naught is positive. So then u of x is 0, is positive on, yeah. So we are just saying that the graph of u will look something like this, okay? All right. Since u double prime x is equal to minus q of x times u of x, and this is positive, right? Because u of x is positive on x naught x1 and minus q of x we assumed is negative, so minus q of x is positive. So therefore this thing is positive. And u dash x, so, so since u double prime x is positive, this implies that the slope keeps increasing, right? This is my x naught, this is my x1, right? And so this statement is telling us that the slope is increasing on this interval, but if u had to come down, that would mean that the slope, this u dash x, has to decrease. So that is really the contradiction. So I'm saying, okay, I've used Rolle's theorem. By Rolle's theorem, u dash has a 0 in x naught x1, but this is not possible as u dash is increasing on x naught x1. So really the idea, I mean, geometrically we can describe it from this line, that we have proved that in x naught x1 the derivative is increasing, so therefore it cannot come down and go to 0 over here. Okay, so therefore it has at most 1 0 in a comma b, right? So we started with a comma b, and we took x naught, and we assume that there is another 0 x1 over here. So that's not possible. Okay, so I hope that is clear. So I'm sorry, I'm going to speed up a bit. Uh, so the next theorem is, let u of x be a non-trivial solution of u double prime q of x, the same thing. Let q of x be continuous, and q of x is positive for all x greater than some x naught. So after some x naught, so we have, so there's some x naught and there's 0. So q of x, we don't care how it is over here, but after x naught, it should be like positive. And if the integral of q of x is infinite from x naught to infinity, then u of x has infinitely many zeros on 0 infinity. Okay, so let's see how to prove this. So let's assume that u of x has only finitely many zeros on the interval 0 infinity. Uh, then there is x1 strictly greater than x naught, such that u of x is non-zero for all x greater than equal to x1. So yeah, that's obvious because this is my 0, and we are assuming that it has only finitely many zeros. So yeah, so I can just take some x1, which is, and x naught is going to be there somewhere. So we can just, I mean, maybe there are some zeros after x naught also. So we can just take x1 to be very large. Okay. So assume u of x is strictly greater than 0 for x greater than equal to x1. All right. Then u double prime x is equal to minus q of x, u of x, and this is strictly greater than 0. Yes, that is because we have assumed that, so we know that u of x is positive, and we know that q of x is positive, therefore the product is positive, and when we take negative, it's going to be negative for all x greater than equal to x1. Hence u dash x, so u double dash x is, yeah, is negative, hence u dash x is decreasing for x greater than equal to x1. Okay. If we show that u dash x2 is strictly less than 0 for some x2 greater than x1, so let's assume we have shown this. Okay, for some x2, for some x2 strictly greater than x1, we have proved that u dash x2 is strictly less than 0. Then we get for x greater than x2, so u of x, I can write it as integral x2 to x u dash t dt plus u of x2. So this is just the fundamental theorem of calculus, right? Now we just saw that u dash x is decreasing for x greater than equal to x1, right? And x2 is greater than equal to x1. So therefore, this we can replace u dash s, u dash t by u dash x2, because my x2 is here and here my t is here. And u dash is a decreasing function. Okay. But then this, this quantity is equal to u of x2 plus this thing will come out of the integral, and we are just multiplying it. So let me erase this in case you can't see. Right? This u dash x2 is going to come out, and we are just going to multiply it with x minus x2 plus u of x2. Now u of, by assumption, my u dash x2 is strictly less than 0. So there is something which is strictly less than 0, and u of x2 is a fixed real number. So if I take my x to be very large, then this quantity is going to become negative. Right? Thus if x is sufficiently large, then u of x is strictly less than 0, a contradiction, which is a contradiction because we are assumed that u of x has no, it's positive in this region. That was our assumption. But here we have proved that if x is, if we can find some x2 such that u dash x2 is strictly less than 0, then by taking x to be very large, we have found that u of x is strictly less than 0. Let me just look at this. Let's just look at this slide once again. Okay, so we just have to show that there is some x2 large, much large, yeah, such that the derivative is strictly less than 0. So let's prove that. So to show u dash x is strictly less than 0 for some x greater than x1, we put v of x is equal to minus u dash x by u of x. So we look at in this region. So this is okay because u of x is never vanishing on x greater than equal to x1. So we put v of x equal to this function. And v dash we can compute satisfies this. V dash is equal to minus u double dash u plus dot dot. and minus u. So this is equal to this, right? U double dash satisfies that differential equation. So u satisfies that differential equation. So when we plug it in, we get this thing. And this you can easily see it's equal to this. Okay. So once we have this expression, we integrate and we get that we integrate from x1 to x, and we get that v of x minus v of x1 is equal to integral x1 to x q of x dx plus integral x1 to x v of x square. So this is a positive quantity. There is a positive quantity. This is a fixed so we can, let's just take this to the other side, right? So this we can write as v of x1 plus this thing. This is a positive quantity. This is some fixed quantity, and we know that this integral is infinite. Okay, this integral from x naught to infinity q of x is infinite, and yeah, so this is x naught, and the integral of q of x in this region is infinite. Now whatever the integral from x naught to x1, that is going to be a finite number, so therefore it forces that the integral from x1 onwards is also infinite. So that will tell us that uh, yeah, so that will tell us that this thing is tending to infinity as x tends to infinity. In particular, this implies that v of x is, yeah, that's exactly what I've written. V of x is strictly greater than 0 for x large, right? But v of x, yeah, now when we put it into this, v of x is strictly greater than 0, that will mean that u dash x is strictly less than 0 for x large. So, right, so minus u dash x is equal to u of x times v of x, right? And this is a positive quantity because v of x is positive and u of x is positive. So this implies that u dash x is a negative quantity for x large. So thus we have found one x such that u dash x is strictly less than 0. And now, and we have, yeah. So we are already, yeah, we are already proved on the previous slide that once we do that, we are done. Okay, so let's just look at look at the theorem once again. Right. So if q of x is continuous, q of x is positive, and if the integral is infinite, then u of x has infinitely many zeros on 0 infinity. Okay, so let's go. Now we apply this to Bessel's theorem. So we look at the Bessel equation and we make that substitution. So you can check easily that when we convert this to normal form, we have to make this substitution, and then you can check easily that we get this differential equation. Right. So for no matter which value of p you take, right, if you fix a p for x very large, q of x is going to be positive, right? Because this term, for any fixed p as x becomes very large, this term is going to tend to 0, right? And you can also check easily that the integral we can, oh yeah, so you can in fact determine the value of x naught for this, which is going to happen. And you can also easily check that there is going to be an x naught such that for any value of p, there is going to be an x naught such that integral 0 to infinity, there's going to be infinite. Okay. So therefore, by the previous theorem, u of x, and remember we were interested in the zeros of Bessel's function, which are in one-to-one correspondence with the zeros of u of x. So therefore, u of x, and hence any Bessel function has infinitely many zeros on the interval 0, infinity. Okay. Okay. So let Zp be the set of zeros of Bessel function jpx on 0 infinity. Since Zp is an infinite set, it is not bounded. Okay. So that's what we saw. Where did we see that? That's what we saw over here, right? Okay. So let's just go back, right? So therefore yeah. So this means that the Bessel's function, remember, yeah, is defined on 0 to infinity. So the positive zeros will look like, yeah, they will keep oscillating. And if you take any bounded interval, that will contain only finitely many zeros. So we will consider the following question. So we just take this zeros of JPX. So we'll call that set ZP, right? So we just take the zeros of JPX and we order them increasingly, right? So we can just number them. So yeah. So this is X1, X2, X3, X4, and so on. Okay. And we can number this. I mean, suppose I tell you to, suppose I give you a infinite sequence which says that many of them converge to this, and then there is something over here also. Suppose I give you a set like this, then obviously you cannot number it because this will be X1, this will be X2, and so on. And you will exhaust all your, yeah, so you won't be able to, yeah, give these, but I'm give these guys, yeah, you will never reach these guys. Let me put it that way. If you say that I'm going to number them increasingly from here, but that's not going to happen with the Bessel function. Zeros of the Bessel function. That's the point I'm trying to emphasize because of what we have proved so far. Okay. So we can number them increasingly. So, and the question we are interested in is, the next question we are interested in is, what is the limit of xn plus 1 minus xn as n tends to infinity? So we have the zeros of the Bessel function. So this is my x1, this is x2, this is x3, this is x4, and so on. Can we say something about these lengths? Right? Once again, I mean, notice that the Bessel functions are like given by some horrible series. A priori, when we look at the series, it's far from clear whether it has zeros, whether it has infinitely many zeros, etc., etc. So already we have proved two fantastic theorems, which is that the Bessel functions have infinitely many zeros in the interval 0 infinity, and if I take any bounded interval, it has only finitely many zeros in that. Now we are going to address an even more difficult question. Can we say something about the difference of the lengths of the difference of the successive zeros? So for that, we will need the Sturm comparison theorem. So what does that say? So the Sturm comparison theorem says that let y of x be a non-trivial, okay, so be a non-trivial solution of, so this should be, yeah, I'm sorry, I'm using the wrong file. Okay, let y of x be a non-trivial solution of y double prime plus q of x is 0, q of x y is 0, and z of x be a non-trivial solution of z double prime plus r of x z is 0, where, so here is our hypothesis, q of x is strictly greater than r of x is strictly greater than 0 are continuous, yeah. So we will just assume that q of x and r of x are defined for some x not greater than 0. Then y of x vanishes at least once between any two consecutive roots, between any two consecutive zeros of z of x. Okay, so let's just appreciate the statement, take a few seconds and appreciate the statement of this theorem. Yeah, so if we take z of x and if we take its roots, then this is saying that y of x vanishes at least once, right? It may vanish twice, but we don't know. It vanishes at least once. That is what this theorem is saying. Okay, so let's prove this. All right, so let's ignore this. I'm in a bit of a hurry. So yeah, I mean, I'm trying to say that, yeah, you can compare these two equations, right? So the root of this, this sine 2x and this sine x. Okay, so let's prove this. So let's say x1 strictly less than x2 are consecutive zeros of z of x. So we have this is x1, this is x2. And let's say z of x is, let's say it's positive. So assume y of x has no 0 in x1, x2. So we may assume that z of x is positive and y of x is positive on x1, x2. Hence, yeah, so because once again, x1, x2, right? So the slope is going to be positive here and it's going to be negative here. Okay. So we consider this function w of x is equal to y of x z prime minus y prime z. Okay. And when we take the derivative, we get this. W prime x is, we can easily check, is y z double prime. Okay, the main point is you can easily check that the derivative is equal to this, right? Now on x1, x2, this q minus r, we assume by assumption our q is strictly greater than r, right? So therefore, q minus r is a positive function, y is a positive function, and z is a positive function. So their product is a positive function on this interval x1, x2. So when we integrate from x1 to x2, so we have concluded that the derivative is positive, right? So which means that, well, okay, which just means that it's an increasing function. So I just want, this is the conclusion. W of x2 is strictly greater than W of x1, right? But W of x1 is equal to y x1 z prime x1. So z prime x1 is positive, right? And y of x1, we are assuming that y does not vanish anywhere between. We are assuming this x1, this x2, this z, and y does not vanish anywhere. So it's this. So this quantity is positive and this quantity is negative. So a contradiction. Okay, I'm a bit confused. Why is that a contradiction? Mm. Oh yeah, that contradicts this because yeah, this is negative, so this quantity is strictly less than zero, and W of x1, this quantity is strictly greater than zero. So that is just not possible, right? So that is the contradiction. So here, I mean, here we showed that Wx2 is strictly greater than Wx1, but we know that Wx2 is strictly less than zero, and this is strictly less than Wx1, right? So this is the contradiction. Okay. So let's go ahead. So that proves Sturm comparison theorem. So once again, it's a very interesting theorem. The proof is surprisingly easy. It's clever, but it's a priori. If you look at this theorem, I mean, it seems like there's nothing you can say, but you can. But that's not true, and you can indeed say something, and in a very simple way. So let's go ahead. So substituting. Okay, we get this. Okay, yeah, fine. Uh, okay. All right. So this is the same thing again and again. We are looking at the Bessel equation in the normal form, and we are looking at this equation, right? U double prime plus Q of x is equal to this thing. Okay. So if P is strictly less than half, so I'm saying Q of x is strictly greater than 1. This is obvious. If P is equal to half, then Q is equal to 1. If Q of x is equal to 1, then our equation just becomes U double prime plus U is equal to 0. So this is a very well-known equation. So we know everything about it. So there's nothing to be understood. And if P is strictly less than, if P is strictly greater than half, then Q of x is strictly less than 1. I'm confused. Uh, oh, oh yes, because in that case, this is going to be 1. Yeah. So this quantity is going to be negative. Oh yeah. So Q of x is strictly less than 1. Sorry, not less than 0. Right. So if P is strictly less than half, then this quantity is positive. Always. So Q of x is strictly greater than 1. If P is strictly greater than half, then this quantity becomes negative. Right? So Q of x is strictly less than 1. So now we use z plus z double prime plus z equal to 0 and Sturm comparison theorem, and let yp be a non-trivial solution of the Bessel equation. So then we get, so let's see what we get. If p is strictly less than half, then we have that Q of x is strictly less than 1, right? So yeah, so which means that between any two roots, okay, so yeah, what was it? So let's just look at the Sturm comparison theorem once again. Yeah. So between any two roots of the equation, which is a solution of the one in which we have the smaller coefficient, lies a root of the equation in which we have a of the larger one. Okay. So that's one way we can remember it. Right. So in this case, q of x is strictly less than 1. So that means between any two roots of, no, I'm sorry, I've written the wrong thing. Sorry. If p is strictly less than half, then q of x is strictly greater than 1. Right. So in this case, q of x is strictly greater than 1. And in this case, q of x is strictly less than 1. Right. So here, the smaller function is 1. So we are looking at roots of z double prime plus z equals 0. Right. So between any two roots of this, any solution of this thing, which are exactly functions of this type, there is a root of ypx. Right. This case is not interesting. So let's just forget about this. Yeah. In fact, yeah, here we are just saying that all the difference between the successive roots is pi, which is correct. And this case is saying that between any two roots of ypx, there is a root of alpha this thing cos, because here we have q of x is strictly less than 1. So yeah. Okay. We can say more than the above. Right. So I mean, let's just look at what this statement is saying, right? The statement is saying that, so uh, I mean, where are the roots, if you look at this equation, the roots of this, the zeros of this will be uh, of this type, right? There'll be some gamma, and then there'll be gamma plus pi, gamma plus 2 pi, and so on. Gamma minus pi, gamma minus 2 pi, right? So this statement, this theorem is quite interesting. So it is telling us that between any two positive roots, there's always going to be a root of ypx. Okay, so let's go ahead. Mm. Yeah, let's just stop here. I think this is a good place to stop. I will stop here, and maybe let's see. Yeah, I think I will. If I go ahead now, I'll have to rush through. So maybe I will take this up next time. So we can say more about. So what more do I want to say? I want to say that. So remember that we had written ZP is equal. We had enumerated all elements of ZP as this thing. We want to say that xn plus 1 minus xn, the difference of the roots tends to pi as n tends to infinity. So we are going to prove this really nice result. So I will stop here. If people have any questions, they can ask me. Is there something in any slide which you would like me to explain once again? Okay, if there are no questions, then maybe we can end today's session and we meet on Monday. Okay, someone has asked a question. Yeah. Uh, okay. So, Nikhilesh, can you please? This is an interesting question. Can you please send it to me via email, and I will reply to you. Thank you. The question is it that we can't have second order ODE with, yeah, Nikhilesh, why don't you just ask your question on chat publicly? I don't know, maybe Nikhilesh has left. So this was the question. So how do I send it to everyone? Okay. Oops. Sorry, I'm not able to copy the question. Yeah. So the question was, is it that we can't have second order ODE with solution as polynomial with a root with multiplicity greater than 1, since it would make the Wronskian 0? So let's just assume that the root is 0, right? I mean, so I don't know, what is the differential equation that x square satisfies? So let me stop the recording.